Then we come to our next speaker, Rishi Yoshi from our team. Please go ahead.
Yes. Thank you, Roland. Thank you, everyone, for joining this session. My name is Rishikesh Joshi, and I'm a PhD researcher at the Delft University of Technology. So this work has been done in collaboration with Filippo Trevisi, who is a postdoctoral researcher at Politecnico di Milano. And the initial introductory work was actually presented in the last AWEC, and now this work is kind of summarized, and we present some results and the follow-up strategy regarding this. So to get started, first of all, this work falls under the pointer.
It's not working.
Maybe
Yes.
you have to click once on the slide.
No, something's broken. Just tell me when to forward.
Yeah, you can go a couple of steps. So this work falls under this IEVIN task, which is basically a task made for collaboration between all the stakeholders between the airborne wind community, that is industry and academia together. So we actually thank all the contributors that participated in this work, and this work falls into work package 1, 2 and 5. And for more information, you can go into the website and get to know more about the task. But now to go into the work itself. So why do we need such a reference economic model? So what we know is that the AWES design is basically affected by these 4 major factors, that is the wind resource, the performance of the system in that wind resource, the costs of the system, and the value that is derived from the deployed system. And what we know that the wind resource and performance is kind of well studied between the community, but the effects of the costs and the value are also significant, which drive the design of your system, and that needs to be accounted for. So this work really encompasses the bottom 2 aspects. And then the advantages for this is, first of all, you can benchmark your own models against the reference. So industry can use it to align with the reference, and then the academia can actually use it as inputs from industry to guide their own work. So in this work we basically identify relevant economic metrics which go beyond LCOE. So not just the cost-based metrics, but some other metrics, and then we can really understand what component is affecting how much in the final economic aspects of the system. And then essentially this model and the report that is associated with this model can act a very nice kind of trustworthy and credible input to the policymakers, such as policymakers and IRENA, IEA organizations, and also consultants like BVG, who already did one report on scaling airborne wind systems. And I say credible because this work is a collaboration between multiple partners. I will talk about it later. But currently, so we see how we divide the structure of the cost model that we have. So currently we have main 3 strands. So that is fixed wing fly gen, fixed wing ground gen, and soft wing ground gen. We don't go into the other concepts yet, but it's definitely can be improved. And the AWES costs are divided into these 5 costs. So kite, tether, ground station, balance of system, balance of plant, in which you have further subcomponents such as structure for the kite, onboard generators if it's a fly gen system, propulsion system if it's present, avionics, which is basically the control pod or the control units and all the hardware associated with it, and certain other components such as harsh environment protection, because you might need leading edge erosion protection or lightning protection, things like that. But we have not modeled that, but we in our model we have this as placeholders, and so that people can essentially contribute in this. So similarly for tether, ground station, and balance of system, we have different substructures. I think we can, yeah. So and you see that the kite, tether, and ground station fall under the one single system category, and then the remaining components for the system are formed in balance of system, which is the site preparation cost, foundation costs, operation costs, installation, and decommissioning. And when we start talking about clusters of systems, then we come into the balance of plant cost, that is the array cable, substation, and grid integration. But we have not modeled the balance of plant yet. It's just a placeholder in the model. So how did we develop this model? So it is a collaborative effort between the many OEMs, suppliers, and universities, and all the data that we received is handled by me and Filippo. So how we did it is that we prepared initial version of the report and the model. Then we provided this to certain number of participants who showed willingness in collaborating, and then we received back their inputs in terms of their quantitative and qualitative both feedbacks, which we use to process and get to cost functions and statistics. In the end, then we use these to make basically a code and an associated report, which we both publish open source soon. So we are in the final phase, and the individual specific data that we achieved from all the suppliers and the companies, we archive it with Airborne Wind Europe. So basically that's not accessible. And then we thank all the contributors here. So you see some OEMs, some suppliers, and universities. So it was I think one of the largest collaborative efforts that we have had, led by academia. So from TU Delft and Polytechnico. So now let's this is just the preview of the title page of the report that we are publishing soon, and it will be published through the IEA Wintask, so you will hear about it. And now how to use the model. So I think it relates to somewhat what also what was just shown in the previous presentation of using the performance and the cost model together to get to some metrics that you can again use to change your design parameters and optimize your system. So what you need is some system specific inputs and some site specific inputs, and also coupled to a performance model. So the economic model has to be provided with performance data and system data. So I will show you an example of this. So what we are working on is a quasi-steady model, which is a fast and scalable model in which we discretize the real-out length into number of elements, and then solve for each length element a force balance to get to the power curve, essentially. And then this model is implemented in an optimization framework so that you get a maximum electrical cycle power output. So tomorrow I have a poster regarding this, so please come to the poster to get more insights on this, because we also perform a sensitivity analysis. We vary many parameters and take a look at how performance is affected by these parameters. But once this is coupled to the economic model I showed, to generate some results, what we simulated is an example of a fixed wing ground generation system. Here you see on the left a power curve of a 2 megawatt system and the system data that we used for the simulation. A wing area of 150 square meter, kite mass is 9 tons, so it's quite heavy. The tether mass at the rated wind speed, deployed tether mass at the rated wind speed around 1.2 tons, tether diameter of 3.1, CL max, and some certain other parameters here. What would be interesting to see is the generator size, which is 4 megawatts, which is quite high because you have the reel out maximum power and you have the cycle average power of 2 megawatts. So now some results. In this, on the left, you see a table summarizing some metrics. The capacity factor is 0.49, which is kind of reasonable in terms of the power curve that we are having on the system data that we have simulated. The LCO here you see is 186. The number itself is not actually relevant. It gives a good order of magnitude, but it relies on many assumptions that are behind the performance model and the cost model as well. So and more importantly, the system that we evaluated is not optimized. So really you could change the use case of this model essentially now to go into the iterative process of how to minimize the LCOE by changing the tether diameter, the wing size, and all the other parameters really. So in this particular iteration, what you see the pie chart on the left is the distribution of the capex, the capital cost, the initial investment cost, and you see the kite structure is almost half, 50% of the total initial cost. Then what is interesting to see is the ultra capacitor cost. So this is something that we have used because of the power smoothing requirement that we need to have. So the ultra capacitor bank is used as an intermediate storage buffer for the reel out and reel in phases to provide us a smooth power output at the grid side. and that basically drives really the cost of the system, as you also see it in the operations cost. So the central pie chart, where the tether replacement is actually 70%. So the frequency of tether replacement, what we find here, is almost actually more than once a year. And the driving factors for the tether replacements are really the bending under tension. And it really scales quite fast with the number of bends that you have per cycle. So if you have one drum, one sheave, if you have two sheaves, it really scales quite fast with the bends that you have with a loaded tether. And the ultracapacitor costs are also significant because you have to replace the ultracapacitor after a certain life. Usually there are 1 million cycles, but we reel out and reel in every 60 seconds almost. So you really fill up the lifetime of the ultra caps, and you have to replace them maybe once in 2 or 3 years. And then you see a LCOE split, where again you see the kite structure cost. Now I'm confused from the colors, but significant costs indeed are the tether and the kite structure. And I think the tether is actually a larger portion in the LCOE because of the replacement costs that you have. So things like these can give you a lot of insights in terms of how do you want to design your system. So if we go next slide, all together, it's fine. Yeah. So the first point what we see is how can the model be used to guide the development is, first of all, to identify what drives the cost. In this case, we saw it was kite structure. So maybe it tells you that you need more innovation in the kite design. Then ultracapacitor bank, that is the power smoothing requirement, was really driving the cost as well. So maybe we want to think on how to reduce this, maybe flying differently, so compromising on certain parameters but gaining on certain other parameters. The tether replacements due to bending fatigue was high. So maybe now you have to size the tether differently. Maybe you have to use even a larger tether. So you have to trade off with performance for the replacements that you need to have. So these decisions really will affect the design of an optimal system, let's say. And the second point correlates is choosing the right kite tether generator combination, because essentially you could use a bigger kite which will give you a higher power, but it has a cost penalty associated with it, which you need to really reevaluate, and it's only captured in something like LCOE, where you normalize the cost and with the energy that the system produces. And further down the line, such a model can be used to identify target markets, because you can really define certain market characteristics, market scenarios, and evaluate n number of business cases where you can see what kind of system fits best in what kind of market. Yes, so some concluding remarks. So what we have now is a model which can enable design for LCOE. And what I didn't talk about is also some other relevant metrics, for example, profit-based metrics, which makes sense when you have fluctuating electricity prices. Then sometimes it's better to produce electricity when the prices are high, and it's usually at low wind speeds. So if you make this as a design objective, and if you start designing your system for a different metric, you'll have a completely different system design. And then, as I mentioned, this can be used to inform many organizations such as IEA, BVG. We are planning to publish, we are publishing this model open source through Zenodo and GitHub repositories. So the DOI, the official DOIs will be publicized through the IEA Wintask and maybe also through LinkedIn. But the key thing is, as this is a first version where we have all the placeholders and some kind of sensible estimations of cost of all components, but the key is to improve this in a collaborative way. So we invite everyone to use and also update the model. Thank you.
Thank you very much. Are there any questions?
Thank you for the presentation. My question is, in the model that you will publish, will it include an optimization block, or it just input output and you use it to to
It's a
manually check.
Yeah, it's an input-output. It's intended to be coupled to optimization frameworks, which I would be doing myself because I have a performance model. I couple the economic model and then use it in an optimization framework. But we publish the model as a individual block, input-outputs, where the user can choose how they want to use it.
Okay, and
So-
for you, how do you use it? For example, just to have an idea, how do you exploit this model in order to optimize design, for example?
Can we go back a few slides where how to use the model as a flowchart? Yeah. So basically, you have a certain inputs design space that you have system-specific parameters which define the kite parameters, etc. Then it's basically a model chain where you use here. What is missing is a loop from outputs to inputs. Essentially, you optimize for any metric that you choose, and then you run it like this by coupling to a performance model. I don't.
Okay,
if this
thank you.
Thank you. One more question, Max. Question.
Thanks very much, Rishi. It's nice to see now this example to get a better feeling.
Yeah.
I was surprised that the operating costs were about almost $1 million per year for a 2 megawatt system.
Yeah.
That largely depends on the tether costs. Are tethers so expensive that you really have these high
The
costs?
model that we have, at least right now, we also have built based on the inputs that actually one of the tether manufacturers has given us. The tether life is heavily impacted by many factors. For ground gen is actually the bending that happens every cycle. For fly gen it's creep. It's different drivers for different systems, but essentially the tether has to be replaced quite frequently as far as our estimation is right now, and that is really expensive.
So we would another way to reduce the cost is to get cheaper tethers.
Yes.
Okay, thanks.
Okay, thank you very much again, Rishi.